And we will move on now to our final presentation for this morning session. I would like to introduce Zexia Li and Celina Trang of Guelph University to talk about their project.
Hi, everyone. I'll just start sharing my screen. Okay, Celina, do you want to get started?
Sorry, muted there.
Yeah.
Hi, everyone. My name is Celina. I'm a current master's student at the University of Guelph, and this is my colleague, Zexia Li.
Hi, everyone. My name is Zexia, and I'm another master's student on this project. We both work under the supervision of Dr. Emmanuel Arnold, Dr. Asim Biswas, and Dr. Jenna Levison. And we will be presenting some of our preliminary findings for the project, which investigate the land use conversion impacts from forest to agricultural land on the soil and water dynamics in the Highway 11 corridor. So due to climate change, the growing season in Northern Ontario has become longer. Plus, the land price in Southern Ontario is becoming more and more expensive. This provides us the opportunity to explore whether there's possibility of expanding the agricultural activity in Northern Ontario. This project is funded by OMAFRA, which aims to provide the baseline data for the soil and shallow water dynamics under the impact of land conversion. And in this study, we're interested in three land uses: forest, crop, and pasture. And the existing forest here represents the pre-land conversion condition, and the existing crop and pasture are compared to the forest land to study the changes resulting from clearing forest and establishing crop and pasture land.
So here I have provided a simple soil conceptual model showing the three land uses of interest in the study. With the forest land use as our baseline and reference land use, we use this to compare the changes in the compaction, which is the soil compaction, and the nitrogen and carbon in the crop and pasture.
And here is the conceptual model showing the main processes controlling the shallow water quality and quantity on each land uses. According to past research, with land change from forest to agricultural, the changes in root zone could alter the preferential pathway of groundwater flow and the permeability of the soil. Previous study also indicated that land conversion has an impact on evapotranspiration, water runoff, and infiltration, which in turn would impact the quantity of shallow water. Also, with different vegetation and management method, the nutrient content in the shallow water system would also be different. However, the impacts vary with climate, soil, geology, land use, land management condition. In this study, we will be investigating whether there are changes in this shallow quantity and quality after a long time land conversion in this northern specific clay-rich setting. So with our background information and the objectives in mind, we select two farms along the Highway 11 corridor, one in Kapuskasing, the other in Borreda. We consider the surface geology, soil type, conversion history, land use of interest, current agricultural operation, accessibility, and whether the landowner would like to participate when we selecting the site. So both farms have the forest, crop, pasture land we're interested in, and those land are situated on typical geology and soil type of the Highway 11 corridor in the Cochrane district.
So to give more reference, we have some instruments here that we use during sampling and data collection during our field season. At the top left, we have mini wells, and these were used to collect groundwater depth as well as use for groundwater sampling. Below that is the Getting Soil truck provided by OMAFRA. This helped us take soil cores down to a depth of 1 meter so we could take them back to the lab and analyze them. To the right of that is the Guelph permeameter. This is a water infiltration measurement that measures how fast water infiltrates the soil surface. And beside that is the motorized hand soil core. So where the truck could not make it into the forest, we had a hand core that also did something similar and also went to a depth of 1 meter. On the right top, that's a lysimeter, and that used suction to pull soil water from the surrounding soil to give us soil water sampling. And below that is a rain gauge. We installed this in the Valrita site because in Kapuskasing, there was a rain gauge already installed at a nearby airport. And so to get local precipitation data in Valrita, we installed our own rain gauge. Moving on to some of the results, to talk about the Kapuskasing soils and the general trends that we found, if we use the forest as our reference, we found that the soil was not very compacted, had high moisture content, and many deep roots that were established and seen in our soil cores that we extracted. The cropland soil had the highest amount of compaction and the lowest amount of water content. Pasture had the lowest amount of soil compaction over the 3 sites and the highest moisture content, as well as a high organic matter layer on the topsoil. Overall, these results on these sites followed the expected trends that we expected to see in this area. In the lower left corner, that is our sampling scheme for how we collected the soil cores, and we attempted to do a transect to capture any soil variability at the site. To the right of that is an image of the lab core, split open so we could do some analysis on structure as well as any interesting geological formations. In the Valrita site, comparative to Kapuskasing, there were quite some differences. For example, the forest had a lower moisture content and a higher compaction than expected. The cropland had similar compaction rates to the forest soil and an interestingly high moisture content in the topsoil. The pasture had a very low amount of soil compaction, but an extremely high soil moisture content. This is similar to Kapuskasing, as well as the fact that it had a rich organic topsoil. Some of the results in Valrita did not fit with the trends that we were expecting to see, however. And so further analysis is needed to inspect as to why this is happening. Each of those points has been marked with a little asterisk. In the soil image below, this is a pasture core from Valrita, and you can see the very dark topsoil that we found in the pasture site.
So using our instrument on site, we were able to quantify how easily and how fast the water travels through the soil. We noticed that at the forest sites of both farms, there was this like a permeable organic rich sponge-like layer there. So water moves very easily through the top 6 centimeter on the forest sites. But this is not the case for the crop and pasture side, and this could increase the runoff on those 2 converted sites. So in general, based on our preliminary finding results, the groundwater moves through the soil more easily near ground surface, and the groundwater travels in a quite slow speed in the area. And the slow travel speed of groundwater suggests that the water quality we observed today in the field in the groundwater may come from a long time ago. So we also monitor the groundwater level on both farms from summer 2019 to spring 2020. So here is the result for Kapuskasing water level relative to ground surface. And on the right-hand side here is a site map which shows the installation, the land use, and also the groundwater flow direction. So for this farm in Kapuskasing, the groundwater flows from southeast to northwest direction. And the decrease in groundwater due to groundwater sampling is circled in purple here. And for the piezometer for the mini well, we installed on the pasture site, shown in the red here, was actually dry in the early part of the study. And in general, the groundwater can be reached about 2 meters below ground surface. Groundwater levels start to increase from summer to early winter. In winter, the groundwater level in the area did not change much, but a slight decrease was noticed on all 3 land uses. And by spring, the groundwater is actually very close to the land surface, where snow starts to melt in the area. Notably, compared to the crop showing blue and the pasture showing red here, the forest set showing orange here shows less short-term variability. So here is the water level data at Valreda Farm. Again, on the right-hand side, here is a site map showing the installation, the land use, and groundwater flow direction. So for this farm, the groundwater flows from northwest to southeast direction. And similarly, I circled the sampling purge in purple here. The groundwater at this farm can be reached at a shallower depth compared to the other farm in Cascading. And the groundwater level at the forest site behaves quite similarly as the groundwater level in Cascading farm. And the groundwater is near surface after snow melt, especially at the crop and pasture site here. Although the groundwater level didn't really change in the winter, but we noticed that the groundwater level at the crop and pasture site showed some minor changes, like through short time in the winter. And at this farm, we noticed there are decreasing groundwater in the fall. So for water quality, we tested for both soil water and groundwater for chloride, sulfate, nitrate, nitrite. So chloride can be closely connected to salt application. Sulfate, nitrate, nitrite can be closely connected to fertilizer application. And the good news is that based on our preliminary data set, so for these constituents we tested, none of them exceeding the drinking water limit on both farms. So for Cascading farm, we observed that the sulfate in the soil water is significantly higher at the crop site compared to the other two land use. We also noticed that the chloride level in the groundwater at the pasture site is significantly higher than the other two land use. The nitrate concentration at the crop and the pasture land is comparable to the forest land. And for the Valreda farm, similarly, we observed a significantly high amount of sulfate in the soil and groundwater at the crop site. And the chloride and nitrate concentration in the groundwater is also significantly higher at the crop site compared to the other two land uses. So between forest and pasture, we notice the pasture has higher amount of chloride and nitrate compared to the forest site. So based on our preliminary water quality result, the land conversion in this area has had a variable but overall small impact on local water quality. However, we still recommend wise land use management because these tested constituents might ramp up over time. Celina,
Sorry. The next steps of this project include analyzing the carbon and nitrogen data, which we have extracted from our soil cores. This will also help us determine accurate particle size analysis to help with accurate classification of the cores, so we can extract the percent sand, silt, and clay data. The hope is to conduct a dye tracer experiment on each site that will help determine soil water infiltration pathways to help with modeling.
We will also conduct an isotope test to determine the source of local groundwater. We have sent out the land use survey to the farmers for both selected farms to learn about their past land use management. And the surveys ask questions about method of clearing forest, irrigation, tile drainage system layout, manure management, fertilizing, and so on. We hope to use this survey data to better explain the trend we observed here in our current data. And the survey data, together with our preliminary data, will be used to develop a specific model And the purpose of this model development is to estimate the water balance and nitrate leaching to a water table on each land use.
So for a summary of our preliminary findings in terms of soil, we found that the pasture soil quality is just as healthy, if not more so, than the forest soils that we examined. And similar to other regions, cropland suffers from soil compaction, though this is not unexpected. And ongoing analysis will help us determine if there are any unique differences in the Northern Ontario soils. This will also help us provide information for OMAFRA to develop best management plans.
And also, our preliminary results show that local shallow material have relatively low permeability, where the groundwater also travel in a relatively slow motion. We also noticed that land conversion from forest to agricultural land removed the surface sponge-like organic rich material. Land use type change also changes the evapotranspiration, infiltration, runoff amount, which we also notice like the groundwater level pattern varies from land use to land use. The variability in water quality could, at this point, could be connected to land use type. So thank you for your listening. And here's our contact info in case you want to contact us for further question after this presentation. And we also want to give special thanks to the landowners who participated in this project and OMAFRA who funded this project. We're happy to answer any questions. Thank you.
Thank you, Zexia and Celina. One question, were any of those areas that you sampled, did any of those fields have tile drainage systems installed?
Yeah, actually on the cropland on both farms, we have, like they both installed tile drainage, but they're installed in a different density. And we've already asked them about the details about the layout of the tile drainage system in the survey.
And how does that affect the different groundwater? Does that affect the groundwater in any way? Differences between having tiled fields and untiled fields?
The most significant difference would be the amount of saturation. Tile drainage lowers the local water table in the tiled area, and so it allows for more breathability, more air movement, and so overall the moisture content would be lower as opposed to completely saturated. It's better for crops, of course.
Thank you. For the forest sites at both farms, were these virgin forests, or had they previously been cleared or farmed or logged at any time?
So like based on the current available satellite data, it looks like they are virgin forests, but we did also ask question about whether they were cleared once before in our survey data.
Okay. And then do you have any data on historical water table depth or water quality on any of those sites?
So we do find some well record in the area, but they are like most of them, they are, household well, like which is supplied for drinking water. So like based on my review, I didn't really find like wells that were installed that shallow, like compared to our study, because our study, those mini wells, they were installed like 2 to 3 meters below ground surface.
All right. And so how much does groundwater quality typically vary from year to year?
Actually, it's depending on the constituent, but like in this study, due to the slow motion of groundwater flow in the area and the low permeability of the subsurface material. So for our tested constituent, although they're like changing from year to year, but I'm expecting the change will be very small, but they might ramp up over time as I talked in the presentation.
All right, and perhaps one more question. So what sorts of best management practices could be used to decrease the impacts to water quality that, say, crops have, for example?
The primary one would be mostly nitrate, in terms of nitrate is easily leachable through water. And so best management practices would not only allow farmers to add less nitrogen for more effective use, this would save on cost as well as decrease the environmental effects of nitrate leaching into the groundwater.
So also like adding on to that, we actually for our next step for the isotope analysis, we are going to test about the nitrate isotope as well to figure out the source of the groundwater. So when we determine the source, we could have like, you know, more confident, when we have like more confident on the source of the groundwater, we could recommend appropriate best management plan at that point.
Okay, perfect. Well, thank you a lot, Zexia and Celina, for joining us and for your presentation.
Thank you.
Thank you.